So last time we ended with this Gelfand-Mazur theorem, which says that if A is a unital Banach algebra, and so we have a unital Banach algebra, and if every non-zero element is invertible, then it has to be the scalars, and every non-zero element is invertible. So then A is the scalars. And we saw that this was an easy consequence of the fact that any element has a non-empty spectrum, which itself was a consequence of Liouville's theorem from complex analysis. All right, so today we're going to pick up, where are my notes? Let me grab my notes, I think they're back here. All right, so today we'll continue discussing about the spectrum of an element in a Banach algebra. So we'll see this a lot in this course for operator algebras, that there's a big connection between topological aspects of these algebras and algebraic aspects of the algebras. Well, one algebraic aspect is just, are you invertible or are you not invertible? Right, and so the spectrum, so let me remind you that the spectrum of an element was by definition the set of complex numbers such that x minus lambda was not invertible. So this is a very algebraic set, and we're going to show that it's connected to the topological aspects. Mainly we're going to connect this to the norm in some way. So to do this, we'll start with first a lemma. So this is a baby version of the spectral mapping theorem. So it just says that if we have, again, a unital Banach algebra, and let's suppose we have some polynomial f, some polynomial, so k goes from 0 to n, ak zk, a polynomial. And let's take an element in this Banach algebra, x and a. So then the spectrum of the f applied to x, so f applied to x, by that I mean you just take z in this polynomial and you replace it with the element in the Banach algebra x, so that makes perfect sense. And the spectrum of this can be related to the spectrum of x. It's exactly equal to the image of f applied to the spectrum of x. So we can see the spectrum of f of x from the image of the spectrum of f. So let's prove this lemma. So we'll prove it by showing each side is contained in the other side. So I don't know if there's an easier one, but let's first suppose lambda is in the spectrum of x, and we'll show that f of lambda is in the spectrum of f of x. And so to do that, let's write out what is f of x minus f of lambda, and you see we're going to have some cancellation at the 0th coefficient, because there, when we plug in f of lambda, we just get a0, or f of c, we get a0. So this is exactly going to be the sum. By now k starts from 1 to n, and now we're going to have ak xk minus lambda to the k. But of course now you all recognize xk minus lambda to the k, x minus lambda is a factor of that. So we can factor out an x minus lambda. So this is x minus lambda times some other element in our Banach algebra. But the point is that if x minus lambda is not invertible, which is the assumption, then of course anything times it is also not invertible. So this is not an invertible element of A. Right? So you get that therefore f of lambda is in the spectrum of f of x. So now we need to show, so that shows one direction, that this is contained in this, so now we need to show the other direction. So we'll do this by showing that anything not in this is not contained in this. So let's take something which is not in the image. So we'll take some complex numbers which is not in the image of the spectrum of x. Alright, so then what can we do? Well, now let's look at f of z minus mu. We'll use the fundamental theorem of algebra and we'll completely factor this. So when we factor this, we're going to have the top coefficient, I guess that's an, and then we're going to have a z minus some lambda 1, minus lambda 2, minus lambda. Alright, so it has some factorization. And what do we know? Well, we know that mu is not in the image of f of the spectrum. So whenever we plug an element of the spectrum, we get something non-zero. Well, that exactly says that none of these lambdas are in the spectrum. Right? So since f of lambda minus mu is non-zero for all lambda in the spectrum of x, we have that each of these lambda i's are not in the spectrum of x. So they're in the resolvent of x. But what does that mean? That means that when we plug in x, so x minus each lambda I is an invertible element. And here we've just written now, when we plug in x here, we've just written f of x minus mu as a product of invertible elements. So we get that therefore f of x minus mu, again, x minus lambda 1 minus lambda n is indeed an invertible element, being the product of invertible elements. Alright, so that shows the other direction. So this is the limit. Alright, so now the next thing I want to do is relate the spectrum to the norm of an element. So this is the spectral radius formula. So let's go to the theorem. So again, we're in the same setting. A is a unital Banach algebra. So A unital Banach algebra. And we're fixing some x and A. So then we have a nice formula for the, well, I should give a definition first. So set the spectral radius of x to be the supremum over all lambda in the spectrum of x of the absolute value of lambda. This is the x. So the theorem says that we can compute this without knowing anything explicitly about the spectrum, as long as we know the norms of x and its powers. So then the theorem is then the spectral radius of x is the limit as n goes to infinity of the norm of xn, but then we take the nth root. So in particular, part of the theorem is that this limit exists. Okay, maybe I'll draw a picture which can help to visualize it. So here's the complex plane, and then we have our element x, and it has some spectrum. All we know about it is it's some, non-empty compact set. Maybe it looks like this, maybe it's much more complicated, something like this. And then we have the spectral radius, so I draw this disk right here, and this distance right here is the spectral radius of x. So this is the spectrum of x that I've drawn here. And then we also have the norm of x, or the norms of the powers of x. And what do we know? Well, we know that, of course, we did this last time, that if you're close enough to 1, then you're invertible. So in particular, we showed that the spectrum is contained in the unit ball. As a consequence of that, we had the spectrum was contained in the ball of radius, the norm of x. So we have that this whole spectrum is contained in a ball of the radius norm of x. So we have maybe this ball, maybe it's a larger ball here, and we have that this distance is the norm of x. So it's larger than the spectral radius, or at least no smaller than the spectral radius. So this is the picture that we have going on. All right, so now let's prove the theorem. Again, we'll do this equality in 2 different ways. We'll show that the spectral radius is less than or equal to the lim inf, and we'll also show it's greater than or equal to the lim sup, and so therefore that gives it to us. So first, let's show that it's less than or equal to the lim inf, and that's not hard to do because of this remark I just told you, that the spectral radius is always, no bigger than the norm. So in particular, and we also know what the spectral radius of the powers of x are because of this theorem we just proved here. So in particular, we know that the spectral radius of x to the n is exactly the spectral radius of x to the n by the lemma we just proved. But on the other hand, we know that this is less than or equal to the norm of x to the n. And taking the nth roots of both sides, therefore, gives us the first inequality. We get that the spectral radius of x is less than or equal to the lim inf, as n goes to infinity, of the norms of x to the n, and then take the nth root. All right, so that direction's the easy direction to prove. So now we have the more difficult direction to prove, and the trick is to use the fact that we also proved last time, and that inversion is not only a continuous function, but it's actually an analytic function. So specifically, if we fix some continuous linear functional on the Banach algebra, so then we showed last time that the function which takes z to the phi applied to z minus x inverse, that this was analytic on the resolvent of x. So this is analytic on the resolvent of x, which is the complement of the spectrum. Right? So wherever it's defined, it's analytic. We know that it's an open set, the resolvent. So we proved this last time. So in particular, it's analytic outside this ball of the spectral radius. So that means that we can has a Laurent expansion. Right? So we get the therefore. Let's write out its Laurent expansion. So we get therefore phi of z minus x inverse has Laurent expansion. We can write it as sum as n goes from 0 to infinity of some an over z to the n, and this formula is valid for absolute value of z greater than the spectral radius. All right, we're all happy with that? Okay. But on the other hand, if we're larger than, so that's if we're larger than the spectral radius and magnitude, but if we're larger than the norm and magnitude, then we also know that it's invertible, and we have an explicit formula for the inverse, mainly the geometric series. Right? So recall that if we did this last time, that if the absolute value of z is greater than the norm of x, so then, well, then that just means that the norm of x divided by the absolute value of z is less than 1, which meant that we had a formula for the inverse, 1 minus x over z inverse was exactly the sum as n goes from 0 to infinity of x to the n over z to the n. Alright, so now if we pull out z, so we have another formula, and if we apply phi to it, we can apply this element-wise, this is absolutely convergent sum. And so now we can find another formula for this, so we get that therefore phi of z minus x inverse is equal to what? So we pull out 1 over z. So this is 1 over z. Now we have the sum as n goes from 0 to infinity of phi to the xn over z to the n. Alright, so this means that, and this is valid, this formula is valid for absolute value of z greater than the norm of x. But now here, at least larger than the norm of x, we have two Laurent expansions for the same function, so we know by the uniqueness of the Laurent expansion that they're the same coefficients. Alright, so we get therefore, that we have a formula for an is equal to, I guess there's a shift here, so it'll be phi to the xn minus 1. I think so. Alright, something like this for large n. Okay, so what do we have now? We have with this power series here that this is absolutely convergent whenever z is greater than this, and we have explicit coefficients. And so therefore, in particular, since it's absolutely convergent, we know the coefficients and absolute value go to 0. So we get that therefore the absolute value of phi xn minus 1 over z goes over z to the n goes to 0 as n goes to infinity. And this is true whenever z is greater than the spectral radius. Alright, but that should just about finish the proof for us. Because in particular, this says that if we take the nth roots here, then we get that whenever z is greater than the spectral radius, if we take the, so one more thing, that since this goes to 0, and this is true, so this is whenever z is greater, absolute value of z is greater than the spectral radius, and remember that this was for an arbitrary linear functional. Okay? And alright, but that means that here the sequence xn over z to the n satisfies the property that you apply any linear functional to it and it goes to 0. By uniform boundedness principle, that tells us that in norm this goes to 0. So therefore, we have that the norm of x to n minus 1 over absolute value of z goes to 0 as n goes to infinity. Again, whenever z is greater than spectral radius, and this is by the uniform boundedness principle. And then this finishes the proof, because we have therefore that the, what was our claim? That the spectral radius of x, so we already proved up there, was less than or equal to the lim inf, but we get now that it's greater than or equal to the lim sup as n goes to infinity of the norm of xn to the 1 over nth. Because if this wasn't greater than or equal to it, that would allow us to choose some z such that this cannot hold. Okay. Any questions about that? So that's the spectral radius formula. It has a nice consequence, especially for C-star algebras, because C-star algebras, we know how to relate the norm of a power to the norm of the element in many situations. So specifically, here's a definition. We'll say that x and a, so at this time we need a Banach algebra with an involution. So if a is a Banach algebra with involution, so then x and a is normal if x star x is equal to x star, so x and x star commute, and x and a is self-adjoint if it's actually equal to its adjoint. And obviously self-adjointness implies normality. And now we have the following consequence of the spectral radius formula, and that is that if x is self-adjoint, or if x is normal, so then we get that the spectral radius of x star x is bounded by the spectral radius squared. Moreover, if we have a C-star algebra, so this is true for any Banach algebra with involution, and if we have a C-star algebra, A is a C-star algebra, then we have equality. And this is, of course, very nice because these are easier to compute the spectral radius of self-adjoint elements. X star x is always self-adjoint, of course. So let's go ahead and give a proof of this. And this is a very easy consequence of the spectral radius formula. So mainly the spectral radius of x star x is the limit as n tends to infinity of the norm of x star x to the nth power, and then take the nth root. But of course, x and x star commute since they're normal by hypothesis, which means we can rewrite this as the limit as n goes to infinity of the norm of x, and of course taking the adjoints commutes with powers, so you can write this as x to the n star x to the n, and 1 over n. Now we can use the Banach norm estimate, so this is less than or equal to the product of these norms. Use the fact that the involutions are isometric, and so we see that this is less than or equal to the limit as n goes to infinity of x to the n 2 over n, which is the spectral radius of x squared. Moreover, if we have a C-star algebra, then the only thing in this inequality we have right here is, notice that here we can use the C-star algebra identity, which says we have equality here. So this is equality in a C-star algebra. All right, so we can compute Yeah, so if we have, so we have this nice relationship between the spectral radius of x and the spectral radius of x star x. And like I said, this makes computations a lot easier, especially in a C-star algebra, because on the left is always a self-adjoint element. In fact, we get the nice proposition directly from this, and that is that if A is a unital C-star algebra, and X and A is normal, so then the spectral radius of X is exactly equal to the norm of X. So this picture I drew here for normal elements of a C-star algebra, this is equal. So if you drop the normality assumption here, this is not true in general. In fact, I'll leave it to you guys as a nice exercise to construct inside of B of H an element whose spectrum consists only of the 0 singleton, but it's a non-zero element. So this is a nice exercise to think about. It's not difficult to do. Okay. But for normal elements, this can't happen. We always have this equality. So let's go ahead and prove this. So let's first prove this for self-adjoint elements. So first, suppose X is self-adjoint. How does that help? That helps because we can now have that self-adjoint implies normal, so we can